Hi everybody, I'm Bill. This video is about a novel method for solving celestial navigation using a sphere and Newton's equations. That's right, by combining two of the things flat earthers hate and fear the most, spheres and Newton's equations, you can solve celestial navigation, and I will demonstrate to you how, and I will show you an application that I wrote to do so. Now, some of you may be old enough to remember a time when YouTuber MC Toon gave a challenge to solve a celestial navigation problem using only a flat Earth. And if you could do so, you could win a big prize. Like you, I knew it wasn't possible, so I didn't really pay attention to the details of it at the time. A few months later, having gotten no submissions for the flat challenge, Toon issued a similar challenge, but now you could use sphere geometry. It was then that I came up with the solution that I'm about to show you. So let's start by solving that problem as a demonstration of how the software works. In the celestial navigation problem, we are given the angular heights of three known celestial objects above the horizon and the times at which they were observed. The solution is the position of the observer in latitude and longitude. The first step is to find a nautical almanac listing for the time the observation was made. It's very easy to find a nautical almanac online. Find the date for which you took the observation, find the celestial object, and copy the values directly from there into the user interface. After copying the sidereal hour angle and the declination for the object out of the almanac, also add in the time you took the observation and the angle it was above the horizon. The program will think that it has enough information to know where the object was in the sky, so it points a big arrow at it. For convenience, we load the rest of the values from a previously saved file. Now we just need to select a view and click Solve. The program finds a point that simultaneously matches all three angles as best it can. The final solution is displayed in the bottom right-hand corner. It also displays the angles between the observer's zenith and the star positions. Now let's compare the results we got with the expected results. After seeing how cool it is, you probably want to download and try this program for yourself. If so, here are a couple of undocumented keyboard commands before we continue. If you're in the left window and you happen to mess up where your view is, like by panning it around, and you want it to be recentered, just hit R. If your focus is in the right window, you can hit F to toggle between full screen and window. Now let's look at another example. This example comes from YouTuber Ruhif's video on why celestial navigation only works on a globe. You can see that he generates a result that's just off the west coast of South Africa. Now let's try our method with the same values. We click Solve and it produces a result just off the west coast of South Africa. Now let's compare some of the angles the program came up with the expected angles. If you look at this example, the yellow arc has a 68.11 on it. That should be the same as 90 minus the value that we input, which was 21.91. That turns out to be 68.09, so we're only off by 200ths. Now let's check another one. The purple one is 51.19, and if you subtract the value we input from 90, you get 51.22, so it's only off again by 0.03 hundredths. Well, here's a 2D diagram of what's going on. What we want is our approximation of where the observer is standing, P, to converge on where the observer actually is standing, the little green X. We consider P to be a point mass and apply the error between P and X as a force to that point mass, and we run a Newtonian simulation. In the two-dimensional example we're looking at, there are three errors we have to account for. One is the error of how far the point is from being on the unit circle. So we apply a force relative to how far it is from being on the unit circle. The error force applied to a star is a vector from the ground position to the point approximation of the observer, and the error amount is the difference between the angle it should be and the angle that the approximation is. On the left side of the screen, you'll see the pseudocode that accomplishes this. Let's walk through it. So for the sake of simplicity, we set the mass of this point to be 1, and that way force is just acceleration. Start by initializing the velocity of the point to 0, and the point is just some guess. For our initial guess, we use the average of the sum of the three ground positions of the stars. D is our damping constant, and T is our time step. Our main function here we call Newton. We add up the error force as described previously. Then we add in what's called a damping force. This keeps the point from springing around too much by subtracting a little bit of the velocity off every step. And then we have your basic Newton equations. Velocity equals velocity plus acceleration times time, and then position equals position plus velocity times time. And then we just do that in a loop until our velocity becomes as low as we want it to be. And that's all there is to it. The code on the right is actually from the program, C code. The function iterate on the right there is the function Newton in the pseudocode. I'm sure you can see exactly what's going on there. Very easy. Let's do one final example for emphasis before we leave. This example comes to us from someone called Proto-Thad. Notice that he's giving us way too much information for this program. All we really need is the angle and the time. This program does not use the radius of the Earth in any way. It doesn't use the 69 or what, the 60 nautical miles per degree. Doesn't use that. Doesn't need any of that. It's just going and finding directly the point that matches with the angles. This program is a 2 megabyte download off of my Google Drive if you'd like to try it. I think you need to run it on Windows 10. Questions and comments, welcome. Thanks for watching.